Your isolation.
Yeah. Use a good Beijing. It's much safer than
Yeah. Safer than here.
there and here. It must be, I mean, Boston must be getting much more serious, otherwise Harvard would not do this. There must be non-disclosed information.
Do you know which executives at Biogen were sick? Was Wally Gilbert sick?
Google closed down, and several biotech companies in Boston closed down.
Today we are very happy to have Zhengwei Liu from Zhengwei University, and he's visiting Harvard right now. And he will be talking about quantized graphs and quantum error corrections. Let's welcome Zhengwei.
Thank you for attending this special seminar at this special time. It's great to be somehow to continue research at this time. And I'll talk about quantized graph and quantum error corrections. And so first, the idea is, if you look at the topic, if you forget the quantized and quantum, just look at graphs and error corrections, then actually you'll find a lot of papers in the literature. Graphs has been known to be very important in constructing classical error correcting codes in computer science. The main idea from this topic is to say, okay, how do we quantize those ideas on graphs and apply those quantized graphs for quantum error corrections? And in this talk, I will show you there is a very natural quantization process, such that the ideas coming from classical error correction theory will be naturally quantized. And actually, there are some known concepts that are already quantized, mostly on the algebraic level. And we'll see those graphical quantization are compatible with the known algebraic quantization. So first, a quick summary of the result. Just give me a four-valent graph. And I think people will have very good four-valent graphs in your mind. And I can return your optimal graphical quantum error correcting codes. This is actually a machine. Once we start with the graph, this four-valent graph, and we consider that as a quantized graph. And then there is general machine to construct the optimal error correcting codes on the graphs. So we'll see more details about the concepts. First, let's review some elementary concepts for error corrections. The basic code is the repetition code. So if we have a bit given by 0 and 1, and we want to store it in some memory, and we know error may happen that will flip the bit, flip 0 and 1. Then how do we correct error? The very basic idea is to say, okay, we repeat this information 3 times. And then we have this triple, 0, 0, 0, or 1, 1, 1. And if the error happened at 1 bit, and then we can recover the information by looking at majority. This is a toy model for classical error corrections. And people have used various ideas to explain this phenomenon. For example, what we want to know is this space 0, 0, 0, and 1, 1, 1, logic bit. And we can describe that using a linear system. Say, we can consider the value as B1, B2, B3 of the 3 bit. And then 0, 0, 1, 0, 1, 1, 1 will be given by the solution of this linear system. And if you look at the coefficient, you get this matrix A. So usually we just represent the code using this matrix. So that's one way to do it. There's an algebraic way to do it. And there's also graphical representation of this matrix given by the triangle. So how do we read the matrix from a triangle? For each edge, we consider that as a bit. And for each vertex, we consider that as a relation. So for example, this vertex here is adjacent to the first and the second edge. Then we read the vertex as v1 plus v2 equals to 0. And here we have 3 vertices, so we get 3 relations. And this is a very classical notation for error correcting codes. And how do we understand the ability of this code? So here we know the code can correct a single bit error, the bit flip. And there is a concept to capture the ability of error corrections called distance. And for classical code, somehow the distance minus 1 over 2, this is the number of errors you can correct. So in this case, the distance is 3. Somehow double the number of the errors we can correct. And actually from the graph, we can read this number 3. How do we get the number 3? It's the smallest cycle. So look at this cycle. It's the length of the smallest cycle is 3. So this has been used to understand the distance of the code. In classical error code, one aim is to find such a graph, such that the minimal length of cycle called girth such that this girth is large. And there are many graphs like that, like expanded graphs, Ramanujan graphs. So those graphs are very important in classical error correcting codes. Now, later I will show you how do we quantize this concept, this linear system, algebraically, and how to quantize this graph pictorially. And then show you these two concepts are compatible after the quantization. So first, let's see how do we quantize the graph. So this pictorial transformation is actually simple and is known on a purely graphical level. We replace the edge by a vertex, this right vertex. And we replace this vertex by this region.
Is it ribbon?
Region. Or you can consider that as a ribbon, that's also fine. Yes. But it's this region, and in general, if you have like a trivalent vertex, then it's replaced by a region like this, or you forward and so on. And we consider the graph on the left to be the classical one, and the graph on the right to be the quantized graph.
So this is the transformation from quantum graphs to string theory.
And here, after we do the quantization, you will see each vertex will be 4-valent. So it's connected to 4 edges. And in general, if the graph here is planar, if this is planar, then this is planar. But in general, we don't have to assume this to be planar. Then here we may get some graph in the 3D space. And if we want to project on the 2D space, then we will have some braids, overlaps of the strings. So later we will see there are some graphs that are 4-valent, but they have braids. They are not really planar. In general, we just consider those 4-valent graphs as quantized graphs. And some of them have such pre-quantization, some of them doesn't have pre-quantization, but we will see the full theory really work. And if it has a pre-quantization, then the theory is closely related to classical error correcting codes, known as like the CSS code. If it's not, then it's completely new. So that's for the classical part, and so far this graphical notation is just graph. We didn't introduce further concepts related to error corrections. So we will see how do we add additional concepts. Now let's go through some basic concepts for error corrections. So what do I mean by error correction? In the quantum system, if we start with a qubit, it's usually described by a state, vector state, in a two-dimensional qubit space. And the n qubit will be in the tensor product. And what can we do to the states? We can apply some so-called quantum channels to states. And mathematically, they are called complete positive trace gradient map, CPTP map. And for this kind of topic, you can simply consider just unitary gates. It's unitary transformations on states. And then, say if we want to store some information in the state, and then there may be error given by the quantum channel. Some error may happen. We represent this error map by this phi e. So that's error. And this delta is the encoding map. So this is the space we want to store our information, considered as logical qubits. And this is the physical memory, considered as physical qubits. So we have n physical qubits. We want to store the information as k logical qubits. And the encoding map is given by the alpha. They map from 0 to 0, 0, 0. And given such an encoding map, there may be some error happens, given by this quantum channel psi e. And what do we mean by error correction? So if we have another quantum channel, psi r, the recovery map, and such that when you compose them, you get the identity map on the logical qubits. So that means when error happens, and then you can recover that. And theoretically, there is a result given by GNU on the left hand. It tells you if you have such an encoding map, and then how do you know the errors that can be corrected? They give an algebraic criteria to check that. So if E is a possible error, and they multiply this E and E dagger, and then compose that with this encoding map and dagger. If this is a scalar multiple of the identity, for arbitrary type of errors, and then this error can be corrected. For example, the bit flip is given by the poly X matrix. So here it can be poly X, or if you have no error, it's the identity matrix. So it can also be identity. If this quantization is always a scalar multiple of identity, then the error can be corrected. So based on this condition, we know how to correct errors. There will be a recovery map. But theoretically, there is a problem. Sorry, theoretically it's good, but there is a problem in practice. The reason is the recovery map is a quantum channel, it's a CPTP map. But usually in the lab, we require the map to be local. Namely, we can only have local interactions of particles. So we cannot have a large scale quantum channel acting on all qubits. So that's a theoretical problem. But for some code, this can be fixed. And also for all the codes we talk about today, there are special type of codes called stabilizer codes. And there are other ways to correct error. So here, I just want to tell you there is a general way to describe the codes, how to correct errors, and how to compute the distance for the quantum case. So what is the distance? If you look at this word, given by a tensor product of poly matrices on n qubits, and we say it can be corrected if this multiplication is not scalar. We say it cannot be corrected if this is not scalar. So in the previous theorem, if this is a scalar, then it can be corrected. Here we take the other way. And the minimal length of the word is called the distance of the code. So that's D. So now we have the three concepts. Describe the quantum error correcting code. N is for the physical qubits. K is for the logical qubits. And D is for distance. It has the ability to correct error. So somehow, when we fix the N, we hope K and D as large as possible. The larger the better. So when we say optimal codes, that means, say for example, if you want to fix N and D, we hope to know the largest number of K. Or if you know N and K, we hope to know the largest number of D. That will be the optimal ones. For the error correction codes, the first example is given by Peter Shaw in 1995. So it looks like the repetition code. And in the quantum theory, we just give this linear combination, and that's the superposition of states. We use the same map, it's isometry. So we call this single qubit in this 3 qubit space. And then Peter Shaw shows that if there is an error given by a poly X, then we change X 0 to 1. And then we can correct that. And here the correction is non-trivial. Since you cannot look at the majority because the information is given by the superposition. It's not just 0, 0, 1. It's not a single word. It's given by superposition. But there is a general circuit, some unitary gates, and such that can correct the error, and you get back to the right state at the beginning. And that's the error correction. And Peter Shaw also gave another code using 9 physical qubits. Here we use 3. So give 9 physical qubits and to encode 1 logic qubits. And the distance 3, that means it can correct a single qubit error. Then the single qubit error is not just poly X. It can be any unitary gate on a single qubit, like poly X, Y, Z. And here is the encoding map. It's a quantization of that map in the X basis and in Z basis. We just compose that in 2 different directions. So those are all the results in 1995.
Excuse me. Can I write the encoding map, the second one, in terms of some number like NKD? There.
NKD? The second?
Just like.
Yeah, it's 9.
9. Yeah, not 1, 3 for this one, but how about the second, this encoding map?
This one?
Yeah,
Oh, 9, 1, 3 for this. This one is 3, 1, 2.
3, 1, 2. Okay.
The first one is 3, 1, 2. There's 3 physical qubits and 1 logical qubit, and distance 2. Here distance is 2 means it can correct poly X, the word. Single word. Now, to explain the general theory, the quantized graphs, first I want to say it's not just the graphic notation. It actually has a mathematical theory behind that. When we say it's a graph, it's not just a notation. It can be translated into algebraic transformations. And this is a general concept called TQFT. So you have a map from cobalisms or with some topological data to linear maps. And we gave this such kind of language called qon language in joint work with Arthur Jeffrey and Alex Wozniakowski. And we introduced this language at Harvard in 2016 and published in 2017. And it's a 3D picture language. And in particular, this is designed for quantum information. It works very well to capture the concepts in quantum information. So what do we have for this language? First, in the usual 1+1 TQFT, you can look at surface with boundaries called cobalisms. Those are surface, 2-dimensional manifolds with 1-dimensional boundaries, and they have to be circles. And then in the usual TQFT, it's that given a cobalism, you have a functor. It maps such a cobalism to linear transformations on vector spaces. And for each circle, it corresponds to a vector space V. And different circles correspond to tensor product of V. And the cobalism maps to linear transformation of multilinear transformation of V. And here we have additional data. But not only the surface, but also we have additional strings. Also considered as line defects in general theory. We have strings on surface And the string can be braided. So you can consider that as 2D projection on the surface or 3D pictures in the bulk. And it has additional charges on the strings, like dots. Now, of course, we expect the braid behaves like braid in the 3D space. That means we have all possible isotopics, random master moves, 1, 2, 3, in the 3D space. And for example, the Young-Baxter equation is this isotopy. And in this theory, there are some part that's not somehow different from the usual TQFT. First, in the theory, we assume this map from cobordism to linear transformations to be projectively defined. That means this map is defined, well defined up to a phase. So it's actually projective TQFT. But this is still good for quantum information because when we consider gate on qubits, the gate is usually defined projective. And when we consider vector state, they are states, they are not just vector, they are actually states. So it's also well defined up to phase. So for the theory in the bulk, on the topological side, we don't have quantization, we don't take linear sum. So everything is well defined, projective. And on the right side, on the vector space, we have the linear sums responding to the superposition of states. So one side is projected defined, the other side is a linear theory. So that's one tricky point of this TQFT, it's projective. And it works perfectly for quantum information. And first of all, the factor can be even super, but let's ignore that. And now let's see there are some basic properties about those charged strings and the surface. First, if we only look at the strings and the charges, they are quite similar to the Ising TQFT or Ising category. And in the Ising category, there are 3 objects: the trivial one, the alternating one, and one more with quantum dimension square of 2. And that is the line here. For Ising case, we have 1 and some gamma and alternating 1, 3 objects. And the gamma square is 1 direct sum, is minus 1, the sign object. And here in this pictorial notation, if you look at the red side, this is the usual topological notation. This black line corresponding to the object gamma, and the red line corresponding to the sign. And here usually we consider, okay, if we have a single dot, what's the meaning of that? That means you have this red line go to infinity. And then we have a lot of relations, topological relations, well defined up to topological isotopic. And now we can consider that as some relation for the charge. And for the qubit case, there are additional relations that are not really well studied. Like for this, if we move the charge below, here is very interesting. If we move the charge below, we don't have IDC. It's well defined. If we move the charge above, we get a minus sign. And this is actually not really a topological isotopic on the right side. It becomes some complicated diagrams. And another thing is also interesting and highly non-trivial. The positive grid can be replaced by the negative grid generally, and with additional charges. But clearly, you won't expect such relation in a topological way because you cannot change all of the grids. And this relation is also very useful in computation because if we compute the diagrams in sense of TQFT that includes knot theory, it's too complicated. It will be NP hard to compute. But this relation tells you, okay, you can forget the order of the knots, and then essentially you don't involve the complicated knot theory. Even though it's there, but it can be simplified in this way, and then everything is computable. Actually, it turns out to be very easy to compute the value of such diagrams.
Can I make sure a few things? Just make sure sure I follow. There are two things I'm not sure I understand. Earlier, when you mentioned this cobordism things, and you mentioned there's some projective things.
Yes.
I'm not sure I fully understand. Is there some projective representations?
Yes.
But if you label the lines as some group elements, is there some projective phase?
Yes.
Okay.
Yes. There are.
There are. Maybe you can introduce that part. Not sure I follow. So how does that representation was determined?
Yeah, I'll tell you
Okay.
right.
And the second one is for this icing TQFT, let's say. So there is three objects, right? There's a trivial line, and also there's an icing annual, right, gamma, and there's a fermion, minus
Yeah.
1. So there should be some way to encode the statistics, like the self-statistics or exchange statistics for the icing annual. There should be some phase like EI 2 pi over 8.
No,
Right.
that's different story here. We don't really use that icing TQFT to understand quantum information. This is not the same as the
I see,
usual one.
I see,
It is actually different.
I see.
So we just use the same kind of diagrammatic relation, but we use that in different ways.
I see, I see.
So for this one, first for the projective things, if you look at those diagrammatic relations, you'll see there's no linear sum in the relations. But there are phases. There are such scalars in the relation, but in principle, no linear sum. So that's why we can define this functor projective, namely we ignore the phase. And then it doesn't matter how do you pair the charge, and what's the order of the charge. Since we have those charged graphs in the surface, and there's no specific order like that. And to make sure it's still well defined after we ignore this red line, or we just ignore how do we pair charge. Different our pairing, we will give you a different phase. So, but if we ignore that, it's not well defined in usual sense. But it's still well defined projective. And actually, for talk today, we will only use the projective theory. So everything is well defined in that sense. That's a very tricky part, but it's extremely useful. So those are the relations we call bulk relations. They are the relations for the coordinates, not the linear relations for boundaries. We consider that the bulk relations. And there are linear relations on boundaries. So those are the usual relations, but we consider that in a different way. And there's one more relation that may be more interesting, and it doesn't show up in other literature. So this is the relation related the string and the genus of the surface. So if you are considering a torus and you have a string go around the genus, then you can remove the genus and the string at the same time up to scale. This is still a bulk relation. It tells you how to change the shape of the surface. And again, for topological theory, we cannot expect that. We have isotopics, but isotopic won't change the shape of the surface. This relation will change the shape of the surface.
So excuse me. What you draw here is which version of the graph is the classical or quantum? Because earlier you introduced some map.
Yeah. Oh, here, all the graph will be for the quantum part.
Okay.
All the theory are designed for the quantized graph, so they will be the quantum part.
So is the line here should be a ribbon?
A line here should be the boundary of the ribbon. Like
Okay.
we have this quantized graph. And the line here will be this line. And later we will add charge to the lines.
Can I maybe interpret this way? Are you trying to maybe interpret some graph, and particularly a map from classical to quantum graph,
Yes.
and then encode maybe some category data like tensor category like icing TQFT into it?
Yes, beyond that.
Beyond.
If you don't have the surface, if you look at the local part, like the theory on the Euclidean part, it's the ideal theory. But there are additional theory on the surface. Just not really a human surface. since we don't have complex data, just logical data.
But also the question is that can you change like icing TQFT like data to maybe Fibonacci or some other type, maybe
theoretically, we
some
can do that, and even more general for any MTC, for the translation we can have some general theory, and it's useful to prove some mathematical theory, and we can actually answer some questions in that way. But for quantum information, this special one, is perfectly compatible with the concepts in quantum information. So we didn't pick up those mathematical notation randomly. We designed this because it's compatible with notation quantum information. And actually, at the beginning, we tried to understand quantum information using 2D theory. So there's no surface, there's those diagrams. And then we realized some concepts are not compatible. And then we realized, okay, it's natural to extend the theory from plane to surface. And then we get a 3D theory, and then it works very well. So now let's see, how do we understand, for example, the Shor's error correcting code using such pictures. And we just draw this picture, and this disk is for the input. You consider that as, so first you consider this like trousers with 3 legs as the surface. And it has 4 boundary circles. The top one, we consider that as the input, and the bottom 3 as outputs. So this will be a transformation with 1 input and 3 outputs. And then in this language, it's a TQFT. So for each boundary, each circle with 4 boundary points, it corresponds to a 2-dimensional Hilbert space. So that's for 1 qubit. And this will be mapped from 1 qubit to 3 qubits. And again, if we run this mathematical theory, this map algebraically is the same as Shor's representation code. So this is just a pictorial representation of this code. And now let's see, this code can correct the error, the poly-X error. And then we'll have a pictorial intuition. How do we understand error corrections in such a pictorial way? So let's check this continuous left-hand condition. So his condition said if we have some errors given by E, and then we have this encoding map, that's Shor's encoding map. And we take the multiplication of I dagger, alpha dagger, E, and alpha. The dagger here is the, somehow in this picture language, is the reflection, is the vertical reflection. And this part is the error. So since we don't know whether the error happened or not, so we write this black box. It can be identity map, it can be the poly-X. And one thing that's pretty useful in this language is, since we have 4 lines for a single qubit, so if we want to write a gate for a single qubit, we will have a black box on 4 lines. But here we only draw the black box on 2 lines. The reason is poly-X in this language is given by a pair of charge. This is poly-X, and identity just through strings. So that means no matter it's poly-X or identity, we only need the information on 2 lines. So the other 2 are free. And we won't read such information in other pictorial approach, like the tensor network approach. So this is one advantage. Have those refined information. And this is actually Quantized map, but in a pictorial way. You consider 4 lines as 4 positions for the Majorana fermions, C1, C2, C3, C4. And then you can represent the poly matrices, poly X, Y, Z, as a pair of Majorana fermions. And different pairs give you different poly matrices. So then we can draw a picture in this way, and these 2 parts, the 2 black boxes are unknown. For error correction, they are unknown. And what do we mean by error correction? That means we will have some computation. Those computations are more or less independent of the error. Here we say this is scalar multiple of the identity. So projectively, that means this map is just identity. And in our theory, it's perfect. We just need to show this map is an identity up to scalar. And how do we do the computation? first we use the string genus relation. We can kill the genus by the string at back. We have no black box on the string. And we also kill the second genus. Then what's left in the picture is we have 3 through space and something unknown given by the black box on a single string. And then in this icing category, the single wire is one-dimensional. So it's always a scalar multiple of some through string. And then we get the identity map. So this is a pictorial computation projectively. We can ignore the error in this computation. And this coincides with the concept error correction very well. So this is kind of the baby idea that we should be able to understand quantum error corrections in such a pictorial way. Namely, the error won't affect the computation.
Can I make sure? Excuse me. So what's iota here in this representation?
The iota is the top part. That's 1 input and here 3 outputs. And then 2 error happened. Well, actually 1 error happened, but in this map, we also take the dagger. So 1 error happened here, and we take the dagger, and we take the dagger of the iota map. And then we compose them. And then we can verify this pictorially. And the verification tells you the computation is independent of the black box. So that means the code is independent of the error, this error correction.
What do you draw a question mark in the second, the equality?
A question mark, this means this is a black box. So we don't really know what's this, but whatever the black box is, this always contributes to the scale. So projectively we know how to compute that. That means we can do the diagrammatic computation with errors. And this tells us we can look at error corrections in a pictorial way. But this is good verification. It's not a good design of error correction code. We can verify some known codes in this way, but we don't know how to design new codes. So then we need this new concept, the quantized graph. The quantized graph will tell us how to design good codes.
By the way, just make sure. So the square implies some qubits, right?
Yes.
It's a 2-dimensional Hilbert space.
Yes.
So then is this KL condition, Kneel,
Yep.
Nathan condition, acts on 2-dimensional Hilbert space only for this case?
Yes.
Is that relation more general? You can consider.
And then more generally, here we don't have to consider the icing. We can consider other things from qubit. That will be d-dimensional. Or we don't have to take 4 boundary points. If we take 6 boundary points, that will be 2 qubits. So it's 4-dimensional, and so on. So there are different generalizations, but this one is so far the best one for practical reasons. Now, let's see, how do we understand Shor's code in another way? The diagram outside is a quantized graph. 3 disks with 3 ribbons. That's the quantized graph. Now we add this genus in the middle, and we add this ribbon in the middle with the input disk. I claim this map is also Shor's encoding map. It has 1 input and 3 outputs. This map looks different from that map, but algebraically they are the same. So one algebraic map can have different pictorial representation, and this one is more useful to design error correcting codes. And actually it's even more conceptual. Since the outside part is the quantized graph, and the inside part captures the topological order. So even though this concept was considered by pictorial code at the beginning, but even for Shor's error correcting code, we can use similar idea, this topological non-triviality, to capture logic qubits. So this code is also topological. And then, now if you understand the concepts graphically, we can say this is not just quantization of graphs, but also it captures the concept of quantum error corrections. We can have additional concepts on those quantized graphs. So previously, the edge for the pre-quantized graph is replaced by the vertex of the quantized graph. Now, since in TQFT, we want to consider the vertex as a boundary, as a circle, and that corresponds to a single qubit. So we say this is a disk of single qubit. And in the previous graph, is for vertex now becomes this region. And the vertex corresponds to this linear relation. So now it becomes this region, which gives the, well, now we don't see why this gave a linear relation, but we will see that in the next slide. That's the magic part. And we'll see that corresponds to so-called stabilizers. And the unshaded region, now, the region for the pre-quantized graph becomes the unshaded region. And now in the unshaded region, we input this logical qubit. This is not a parity at the beginning. So the unshaded region corresponds to logical qubit. But in this case, we have this further correspondence. And of course, here we have this shading and alternating shading, and this only appears for planar graphs. If the graph is not planar, then we don't have to input such shading. That will be another story. But now let's see this key part. How do we understand the relation? How do we understand this shaded region? Why it becomes a stabilizer?
Sorry, just to make sure. So are you saying this graph will be equivalent to Show's encoding map?
Yeah.
Or is there, you say there's also additional topological features, topological order,
Yes.
not including Show's encoding map. Are you trying to map to something even different than Show's encoding map, or is that equivalent?
Yeah, if we look at this algebraic map, we don't see topological order.
Right.
But if we look at this pictorial map, we do see this topological order. And later we will talk about the torical. You will see they share the same properties in this sense. The natural part, this cycle. This natural cycle gives you the logical gate. Logical gate. So the key part is after we do this quantization, we not only capture the qubits but also the stabilizers. So what's the stabilizers? Now for the quantum case, we have this space given by 0, 0, 0, and 1, 1, 1. And usually we disconnect by stabilizers. Z1, Z2, corresponding to this relation. For the quantum case, it's not just sum of the bits, but it's given by the action of poly Z on the states. So poly Z1, poly Z2 is identity, acting on 0, 0, 0, or 1, 1, 1. So the three linear relations in the classical case now becomes the stabilizers of the code. Namely, on the logical qubits, those polywords acting on the logic qubits as identity. And in another way, you can describe logic qubit as the solution of such stabilizers. And such codes are called stabilizer codes. So now let's see why this shaded region coming from the vertex at the beginning, why this shaded region give us these stabilizers. So let's look at this shaded region. Let's see how do we get the data stabilizer from that region. For this region, we can add a pair of charge nearby the disk. And the pair of charge corresponds to a poly matrix due to collapse map. Pictorially, this will be a poly Z acting on the first qubit. And this will be another poly Z acting on the second qubit. So applying this poly matrix Z1, Z2 on the qubits It's the same as adding this pair of charge on the graph. One is algebraic notation, one is pictorial notation. And now why this is identity? We rate the charge in a different way. Now we look at the string. For this string, it has a pair of charge. And charge are Mariana Fermis, so they cancel. Two charge will cancel. And on the second string, they also cancel. So you can look at the picture in a different way. Pair the charge in a different way, and then they will cancel. That's why it's an identity map. So in general, once you see a cycle on the graph, and then you can always add the charge in this way nearby this, and then you get a poly word. So the pair of charge are always poly matrix, poly x, y, z. And then on each string, you have a pair of charge. So it's always an identity. In general, we have this concept. Given a cycle on the quantized graph, it gives you a stabilizer of the encoding map. So now this purely algebraic concept stabilizer becomes a very natural pictorial concept. It's a cycle. That's something we know very well.
Excuse me, can I make sure? So you say the black dot, like you say it's a charge that you assign maybe Marana
Yeah.
fermions. Yep. And then when you fuse two Marana fermions, the Hilbert space become at least two-dimensional, right? And how is that encoded? So if you fuse gamma with gamma, you get 1 plus minus 1. So there is
But the Hilbert space is here. Hilbert space here, it's not here. So this is just, that's why I said we use the same diagrammatic relation, but we use the picture in a different way. Not the original approach of answering category quantum information. We use the same set of diagrammatic relations, but really in different, with different interpretation of information.
what will be the fuse mean?
Yeah, fuse means here, if you have pair of charge, it's just a single string. Like C multiplied C is identity.
How do I see this operation? Operation will be non-trivial, or was it a do nothing operation? In the sense, how about what does that imply in this correspondence? Just maybe this identity, I didn't get the essence. The left hand side equal to right hand side.
Yes.
What happened?
So on the left hand side, this means we apply a poly Z1 to the first qubit and another poly Z to the second qubit. So we read it locally. And on the right side, we read it in the other way. We look at the pair of charges on strings, and then we cancel them. So two different computations. And then the two different computations tells Z1 multiplied Z2 is identity. And that means it's a stabilizer of this encoding map. So that's the key part. The stabilizers can be understood in a pictorial way by cycles. And then to define stabilizer code becomes define cycles on graphs. And actually, in general, there are some tricky problems to define stabilizer code. We have to ensure minus identity is not in the stabilizer group. And it's not easy to find such words, such that minus identity is not there. It's a very tricky condition. But here, when we find such cycles, there is no such condition. And this sign is automatically fixed by the graph. That's a magic. That's not true. And constructing cycles on graph are much, much easier than constructing some polywords. And we have tremendous known mathematics related to cycles on graphs. And later we will see how to use group theory, geometric group theory. How do we construct cycles on the Cayley graph? And they correspond to relations of groups. There are many other known mathematics related to cycle on graph, so we have many new methods to construct such chiropractic codes. That's the big advantage to give this different interpretation. So that's really the key. The cycle gives the stabilizer. So we can understand this algebraic concept in a pictorial way.
Oh, by the way, so since you mentioned stabilizer, so the GTAP toric code, suppose I put on torus, you can count the number of ground states,
Yes.
the dimension of the Hilbert space, subspace, by counting the non-trivial cycles on the torus or the stabilizer. So in this case, is there some notion where do I put this? Maybe some quantum system on some non-trivial topology?
Yeah, let me show you. Let's go to the toric code first. So for toric code, we have the square lattice. And now this graph is the pre-quantized graph. You can consider this as the triangle of the classical error corrections. The lattice itself is the classical one. And for context toric code, we have the qubit at the edge. And for classical case, we have bit on the edge. And the stabilizers are given by the vertex operator or placket operator. It's given by the product of poly z around the vertex, or product of poly x around the placket. Or you can switch x and z. And then we take all those loop operators and stabilizers. And then we know the stabilizer states are 4-dimensional. That encodes 2 logical qubits. Now let's do the quantization. Let's see what happens if we quantize this graph. So each edge now becomes the vertex. So the green part on the right side is the lattice. And the black part is the quantized graph now. So each edge is replaced by the vertex, and each vertex becomes a region. Here I ignore the shading. Now this poly z, if you look at it on the right side, it again becomes a cycle operator. So we have this smallest cycle on the quantized graph. And at each vertex, it's a pair of charges, poly z. And if you look at cycle at the placket, we still have this pair of charge. But if you look at the shading, it becomes a different shading. So this is poly z, that becomes poly x. And then we have another poly operator. So the stabilizers on the quantized graph are once again unified as cycle operators. And those are local cycles, means they are contractible. And how do we understand the topological ones? So the graph is really on torus. Now we glue the boundaries as on torus. And for the overlap, we consider that as projection of the 3D picture to 2D, so we have those grids. And then we can capture this non-trivial part using the additional genus and with the input. And here, since we have 2 non-trivial cycles, we can add another genus here and the input here. And that is the 2 logical qubits. And this map itself is the encoding map of context map. So it's not just defined by the stabilizers. Actually, we can define isometry from the 2 logical qubits to the 2n squared physical qubits. And this is the encoding map. And all the properties you want to study can be reformulated on this map. And actually, we can not only define the ordinary toric code, but also the toric code with defect lines. Then they can measure some qubits here in the y basis, then you have defect lines. And there are some other stabilizers. And those stabilizers becomes very weird. Some operations they do not behave like vertex or black hat. But if you have a defect line here, then the new stabilizer becomes this cycle. It's still a cycle on this quantized graph. So just all such concepts, maybe weird, can be captured by cycles in a uniform way. So that's the context code, and it has such natural interpretations. One more thing. For this code, well, later we will understand this code by not in another way. Just how do you understand the small cycle as local ones, how do we understand the global cycle as the topological ones? How do we generalize these concepts? And actually we'll see many other things that are not topological can still be distinguished as this kind of local ones and global ones. Even though they are not topological, but the concepts can be generalized on the quantized graphs. Well, this is for the short code, and for the general 913 code, it has a similar graph. And I will skip that. But this one I want to mention is we don't have to work on planar graph. We can work on non-planar graphs. And the smallest non-planar graph is this graph K5. Each vertex, again, is 4 valid. It's perfect. It's a quantized graph. Even though this graph has no pre-quantization. Now for this graph, if we construct a logical qubit by this graph, so somehow in TQFT you have a graph with 5 outputs, so that corresponds to 5 qubits. And now we can construct another 5 qubits by adding pairs of charge on the edges, so it's actually fully charged. And then we can show they are orthogonal. And actually in general theory we can prove for the charged graphs, the states are either the same or they are orthogonal. So they actually form orthogonal basis. Now in this case, if we look at this charge graph, we get one logical qubit, 0 and 1, given by 5 fitted qubits. And this is the 513 code. It's known as the optimal code to crack single qubit error for one logical qubit. And that's also all the results given by 2 groups in 1996. And they can be described as by stabilizers. Like each stabilizer has 4 polys. And now let's see how do we understand these stabilizers. I don't have that graph. Okay. So for the stabilizers, if you look at the cycle of even length, for example this cycle, and then at those 4 vertices, we will have pairs of charges, and that will give 4 polymetrics. So for all such length 4 cycle, it will give you a stabilizer with 4 polygons. And actually, the stabilizer of such code are given by cycles with even length. And these 4 are generators. So how about the cycles with odd length? If we take the cycle with odd length, then actually on the first graph, on the phase, it will be 1. On the second graph, phase will be -1. So this is logical Z on the logical qubits. And why they are different by sign? Because if we read the number of charge on cycle, it will be odd here and even there. The difference of the parity tells you the difference of phase. It doesn't matter what is the exact phase. We are only interested in the relative phase. So that's why we only need the theory to be projected. When we consider the superposition of the two, we are only interested in the relative phase. And that's captured by the parity of charge on cycles. So from this non-planar graph, we can get the optimal code, 513 code. And then we can expect there are many other good codes given by such non-planar graphs. And that's beyond the planar theory. So somehow this is no longer 2D theory because it comes from graphs in the 3D, projected onto. In general, given such a forward graph, we can always construct the code like this. We consider stabilizers as certain cycles, and we consider the logical qubits as the charge graphs. And the stabilizer fixed the charge graph is the same as the number of charge on cycle is even. Then all such properties are captured in purely pictorial way, and there are many interesting dualities given by pictures. So now I will mention a general construction. related to group theory. So here we want a forward graph. And then in group theory, there's a very natural construction of forward graph. We start with a group with two geometers. And then we consider a Cayley graph. The vertices of the graph are given by group elements. And the edge are given by the relation like from one element to another. Such that it's multiplied by the generator. That's the Cayley graph. Like for the Tauri code, the vertex will be given by numbers x, y in a 2D space, and such that x plus y is even. At the edge, there are two kind of edge. The one edge is given by 1, 1. The other edge is given by minus 1, 1. This edge and that edge. And then we have the inverse. So this is actually a Cayley graph of this group of A, B, B, C. And if we want this to be periodic, then we can say this is Z mod n. Then what's the meaning of the local cycle? Local cycle means we have this relation A, B, A inverse, B inverse equals identity. And this relation tells the local cycle. Now what's the non-contractile cycle? It's here. It's A to the n equals identity, and B to the n equals to identity. So you can understand all those concepts in group theory. And those relations are for this 2D lattice without periodic boundary condition. So if you consider A, B, take value in Z in this bigger group, then okay, you get the local cycles. But if you consider caution of the group, then you get this additional relation. They correspond to the global topological ones. And this concept works just for group theory. We don't have to say this graph is embeddable in a surface. We don't have to say it's topological. It's just a caution of bigger group to a smaller group. The bigger one can be infinity, like the planar lattice is infinite, then the bigger group will be an infinite group. And if we want a code, a finite code, like with finite many qubits, then we take a finite caution of the infinite group. So in this we can really construct a lot of codes using group theory. And why we are looking for group theory? Because the classical error-corrected code is closely related. Like how do we construct such expanded graphs? We use such group theories. And here I give some examples why this is interesting, like the Tauri code we mentioned comes from that way. And the 513 code is also from that way. The bigger group is Z mod 10, smaller group is Z mod 5. This is double cover. That's why for the stabilizers we have the even cycles, because they are given by cycles in the bigger group. Then we project that on cautions. It's kind of a Z2 fiber. And also in general, we can take this geometric one, this group, this triangle group. And then we know that this Cayley graph can be embedded in the homogeneous surface. There's a sphere if this is bigger than 1, the people are a relation. And it has an AD classification. 0 if this is 1. And the curvature is -1 if the sum is -1. And then the surface becomes homogeneous and it's hyperbolic. And then if you look at the corresponding code, we will actually recover all the hyperbolic codes. And actually, people didn't exhaust all possibilities. There are actually more codes coming from this list. But they share similar properties. So in that sense, we didn't really find exactly new code for such graphs. But there are many other new codes, like from group theory or other constructions. Those graphs have good 2D geometric properties. And then for the
I think that's something. Let me just make sure. So, just make sure. So, when we say like a key-type Tauri code,
yeah.
So usually we say there's an underlying quantum states or order associated to it, independent from what's the topology of the space manifold you put on. And well, here there's also a notion in your case, some surface. And is that, for example, like you say there's a Gaussian curvature kappa, right?
Yeah.
And does this distinguish? I'm just trying to understand what's the data here. Is that the data of kappa associated with certain code, or is that data related on which surface?
The data is here. I skipped that. Sorry. The data is given by two groups and the generators. So we have a bigger group. It's two generators, and then we have a finite quotient, and then we look at the Cayley graph. And for the bigger group on the Cayley graph, we have all the cycles on the Cayley graph corresponding to the relations of the group. And then we take quotient. There are still cycles on the finite quotient. And those cycles becomes the stabilizers. But they are not all cycles, so we still have some extra space to encode logical qubits. And here is one example. The bigger group will be like the group in Z mod Z, Z cross Z, and the quotient is Z cross Z. And the relations for the bigger group is this. And for the quotient, we have the additional relation. It doesn't come from here. Those becomes the logical ones, rhetorical. But in general, it's not necessarily tautological. For those, for this group, it's still tautological because this group is very good. Cayley graph can be embedded in a surface, and this is very naturally embedded. Actually, it's a geometric embedded. But in general, if you start with some other groups, it's not necessarily embedded in some surface. The theory becomes more complicated, and essentially it's no longer 2D theory. And this is very important because from the code, we not only get an arithmetic code, we actually get a Hamiltonian model, exactly solvable model. Because we can take those local operators, like in collapse code, we can construct a Hamiltonian, give a sum of those local operators. And then the ground states of the Hamiltonian give you the logical qubits. And clearly, it's just group in general. We can define some local cycles, and then we take sum of local cycles, and then we get a Hamiltonian. And the ground state of Hamiltonian is again the logical qubits. So that's the good part of this code. It can be easily implemented experimentally. Everything is really local.
Can I make sure one thing? So suppose let's take a P-territory code. That's actually you can label with such a quantum state by some good cohomology situation.
Yep.
It's some group, let's say Z2, and a third cohomology group.
Yes.
And
That's
you
for the that's this kind of code.
Right.
Those are quantization of graph on surface.
Right. So how is that data encoded in the data? I think there should be some transformation between.
Yeah, there's transformation.
So
Like
how is
here
that?
we see the cycle.
Right.
The cycles are really just the cocycles in this theory. But there are another part that's non-trivial. When the graph is planar, the dual data is also cycle. Like the graph to the dual graph. But if the graph is not planar, the dual is no longer cycle. And it's captured by so-called bipartite condition on the graph. And that becomes highly non-trivial. But still, it works well in this theory. So that means we can deal with this theory not only for embedded graph, but also for non-planar ones. It really extends this theory. And then it's not really homological. That's why I said for the one that can be embedded in surface is topological or homological. For other ones, non-planar, they are beyond this theory. And essentially, the statistical model is no longer 2D. It's projection of 3D model on a 2D space. And that's the big advantage, since 3D models are very hard to study. And 2D models are more or less well studied. And this is kind of a good balance. Model is 3D, but we can use 2D method to study them. So we can have some additional, but that part is still just for future research. So we can have some additional tools to study 3D models using 2D methods.
That's very good. it's interesting. Let me just try to understand. So maybe the false one, there's false models. I think because it looks like there are some data, for example, for the usual like torical or some twist quantum double model, the data you input will just be say some group and some twist cocycle given by cohomology theory. And that's the data. And independent from what's the manifold, what's the way you put on, what kind of triangulation is used. But here it seems like a false one. There is some data also you input. Is that a P and Q given by the underlying quantum theory, or is that also encoded do you also encode like maybe the topology of lattice?
Yes.
I'm just trying to distinguish what kind of data
exactly. Yes. So that means for the local data, we only have spins,
Uh-huh.
like those charts,
Right.
like spins. But the lattice could be very complicated. It's not necessarily the usual 2D lattice, not the usual 3D lattice. It could be some very weird lattice. And those weird lattices are given by those quantized graphs. That's the non-trivial part. So we can construct some other type of models, and those properties are unknown. And actually, if we change the shape of the lattice, we can see different phenomena. Like for example, we can count the number of ground states. If it's a square lattice goes to infinity, then the number of ground states will be 1. It's trivial. If we take the graph to be a tree, then the number of ground states will be infinity. Just change the shape of lattice, we can get different phenomena. And clearly, this Hamiltonian has gapped in large scale limit. And at one point, I saw why it's not topological. Since many people thought all such gapped Hamiltonian or 2D lattice model will be topological. And here, I don't see any reason it's topological. And then when I talked this with Kong Liang, he said this actually is not really 2D because we have grids with cosy 2D. It's really a projection of 3D model. Then there's no way to expect this is purely topological. And then we can expect many other phenomena. And that actually coincides with some earlier observations. We try different graphs, then we really see different phenomena.
Let me make sure one more thing. So suppose you give me P, Q, R.
Yeah.
Here, is different P, Q, R represent different type of code, different type of order?
Different type of code, yes.
But how is the feature of a curvature coming?
Oh, here, because this is the Poincare triangle.
So just make sure. So this curvature also encode the underlying quantum system, quantum order.
Yes.
This has nothing to do with the topology of the space manifold, right?
It has, because here is the graph. If you don't take a quotient, it's like for the last case, it's on the Poincare disk. But to get a code, you have to take a quotient of this group. And then the graph is on a Riemann surface with Siemens. And then the somehow distance of the logic qubits, logic gates, are given by the topological data on the surface. Then it becomes topological. Since the Cayley graph of this group is still embeddable in the surface in a geometric way. So for the future, there are many exactly solvable models. And we have variable Hamiltonian. It behaves like the K-type story code. And the point is, again, everything is like polymatrices. It seems well understood. And the major difference here is that the underlying lattice could be very complicated. And we don't really know what could happen for those codes. That's for the future study. That's all I know.
Could you comment on what's known about the optimal codes? Finding the optimal codes?
For fixed graph, we can construct the stabilizers by taking a set of cycles. And then the question is, if we fix the distance, how do we maximize the number of logical qubits k? And now we have an algorithm to do that. So that means for every fixed graph, we know how to find the optimal code. for different d, you can change the d. And then for each d, you find the best k. So that's pretty good since I don't think there are other methods to find optimal code in any previous approach. But here we found one. The big reason is for this method, we have a very good way to compute the distance. And what we cannot understand is now the graph itself is still fixed. We don't know which graph will give a good code. The graph is still a variable, which is a change graph. And the expectation will be that graph like Ramanujan graph, this graph with large cycles. But like Torrey code, we don't have to assume all cycles are large. We can have some cycles be small. And they will appear as stabilizers. So we only require those global cycles to be large. So that gives additional freedom in graph theory. So we don't have to use such a strong assumption. Like Ramanujan graph or expanded graph, or some mild assumption. So the graph has some global cycles that are large. Locally they can be small. But still that part is unknown.
What do you hope for as the best bounds for K?
I don't know. At this point, I don't know. There are open questions. Like once here, the Hamiltonian is local. That means the code is low density parity check (LDPC). And the question is whether there are LDPC codes such that the efficiency is linear, like the indicate dk and b linear with respect to n. And there are constructions which are approximately linear but not exactly linear. So that's still a big open question. And it may be possible to construct such code, but I don't know.
Comments is that the kind of a quantum order system for the, I suppose you are trying to build out some kind of graphical way, even for topological order states you can code somewhere. But topological order actually is one kind of a gap, quantum liquids. And there is actually a new type of order for the author was also here in some talk that earlier there's some people talk about fractal order. These are quantum gap, quantum states, but it's non-liquid in some way. I suppose there could be also a graphical way to
Yes, because here, we find some phenomenon. It could be possible because when we look at the possible errors, some of them doesn't behave like the topological ones, more similar to the fractal ones.
Yes.
But we cannot prove that. So we don't have any rigorous proof to show some code constructed this way, unlike fractals. We don't have proof yet. But just for example, by looking at the graphs that, like those graphs, they embedded in the pumpkin disk. The size of graph grows exponentially. And then if you look at the code from that kind of graphs, it doesn't behave like the Torrey code. It really behaves in a different way. Sometimes locally it behaves like the fractal, but in general we don't have proof.
There's a Hamiltonian for those type of fractal models. It's also from this poly matrix. There should be some way to write this poly x and poly z in some way on qubit lattice. Maybe there is some way if you start from, because you have a way to map the graph to Hamiltonian. I don't know whether there's an inverse map from Hamiltonian to some graph.
That's a very good question. I'm considering that, but I didn't get a good answer yet so far. Since now we look at stabilized by cycles, all the local operations are given by word of polys. But somehow we can even take some of such poly words, and then we have the general Hamiltonian. And I believe for many interesting properties, it won't change the behavior of the ground states. But still, it's not a proof. Since here the lattice becomes weird, it's projection of 3D, and somehow it's more or less local, but not really local. They do share properties like that if you have some sum of those local operators, and local operators are given by sum of the polys. Here we assume each poly word is given by a cycle, but in general it could be not just cycle. Like the cycle means it's closed, but we can allow open ones. And then it doesn't have to be like cycle, but the theory is not completed, and I guess that will be more interesting, but I don't know how to develop that.
Any more question, comments? If not, let's thank Zhengwei for a very nice. Thank you. Very nice.
你们学一个他的东西，主要是先学最简单的嘛，